The sampling distribution of the sample mean is the probability distribution of the population of the sample means obtainable from all possible samples of size small letter n from a population of size capital letter N. So the sampling distribution, again, is a probability distribution, meaning this allows us to see all the possible values of the random variable and their corresponding probabilities. However, the sampling distribution does not show us all the possible values for a random variable x. For example, your random variable x refers to the SAT scores of applicants. A sampling distribution will not show us all the possible scores or all the possible values of x. Instead, the sampling distribution of the sample mean will show us the probability distribution of the population of sample means. So in other words, it will not show us all possible values for x, the random variable x, or the SAT scores, but it will show us all the possible values for the sample mean, or the average of values of x. Or in example mentioned earlier, the sampling distribution of the sample mean will give us all possible values of average SAT scores. Now, how is it possible to get different averages? We have here a population of sample mean, so how is it possible to get different values for the x-bar or the sample mean? It's possible by getting all possible samples of size small letter n from a population of size capital letter N. For example, if you have 900 scores in the entire dataset and your sample size is only 30, each combination of small letter n or 30 will give you a unique value for the sample mean. So for example, you can get the first set of 30 and you can compute for its sample mean. Now, it's possible to get another sample mean by getting a different combination of 30 measurements. So maybe you can get the next set of 30 or the last set of 30. If you get all those possible sets of 30 and compute for their sample means, that will allow us to see all possible values of the sample mean, and that is part of the sampling distribution. And finally, to make it a complete sampling distribution of the sample mean, we should be able to see the probabilities for each sample mean. So it will show us all possible values for the sample mean if you are getting small letter n from capital letter N, and the respective probabilities of each of those values of x bar. Now I'll show you a simple example on how to construct the sampling distribution of the sample mean given a certain population. So my population is composed of just 6 elements. We have 6 stocks, and for each stock, we have here their respective rates of returns. So for stock A, the rate of return is 10%, for B, it's 20%, and so on. So this is the population. I only have capital N equal to 6. And if I compute for the average rate of return of all the 6, I get 35%. Now we can construct the probability distribution of this by computing for the relative frequency of each element. So this can be considered as the random variable x, and here I'll put the probability for each value of x. So if you randomly select 1 out of the 6 stocks, the probability for each will be 1 over 6. So it's a constant from across all the 6 values of x, and this is your probability distribution of x. Now it's different again from a sampling distribution of the sample mean because we are not getting probabilities of each value of x, but the probabilities of each value of x bar. So in this example, I'll use a sample size of 2, and in order for us to compute for the probabilities of each sample mean, we need to get all possible sample means first. So if I'm getting small letter n of equal to 2, from capital N of equal to 6 that will allow me to get these combinations. So using the combinations function, that's 6C2, that will give us 15, and all those 15 are listed here. So it's possible to get stocks A and B, and that's shown here, or I can also randomly select stocks A and C if I select 2 out of 6, and that's shown here. So for each row here, that's one possible combination of 2 out of 6. And now I'll compute for the sample mean of each of these combinations. So sample mean, or x bar, so that's just the average of the two. So for the first combination, my average is 15%. And then I'll do that for all the other combinations, and you will get here all possible sample means. Now, although we have 15 different combinations, we can see that we don't have 15 unique sample means. You can see here that some sample means appear or occur more than once, and in order to construct the sampling distribution, we need to list down all the unique values for the sample mean. So here we can see that the unique values are 15%, 20%, 25%, 30%, 35%, 40%, 45%, 50%, and 55%. And in order to get the probabilities for each, we can start first by getting the frequencies. So the frequency for 15 is 1. It only appeared once. 0.2 appeared once also. 0.25, however, appeared 2 times. We can get an average of 25% in 2 cases if you get stocks A and D or stocks B and C. So the frequency there is 2. Now for 0.3, that's also 2. For 0.35, 35% appeared 3 times. For 40%, it appeared 2 times. For 45%, it also appeared 2 times. 50% only happened once, and 55% also happened only once. And if you get the sum of all these frequencies, we will get 15 because we have 15 different sample means. Now, in order to get the probability of each sample mean, we can simply compute for the relative frequency. So that's just the frequency for each value of x bar, or the sample mean, divided by the total number of sample means, which is 15. So doing that for all the possible values of the sample means, we will get the following probabilities. And if you get the sum of all these probabilities, we will get 1. Because again, the sampling distribution of the sample mean is a probability distribution. Therefore, the sum of all the probabilities should also be equal to 1. So that's how we construct the sampling distribution of the sample mean using this simple example. Now, aside from knowing how to construct the sampling distribution of the sample mean, you also have to know how to interpret the sampling distribution of the sample mean. For example, if we look at this row, we have 35% for the sample mean and the probability is 20%. You should be able to interpret these values. So how do we interpret this? Again, 35% is a possible value of the sample mean, and the probability of that is 20%. Now remember, the sample mean 35% is just one of the many possible sample means if we get a sample size of 2 from your population of 6. So that is necessary for us to interpret the probability. So again, this means that if we randomly select 2 stocks out of the 6 stocks in the population, the probability that the average of the 2 stocks you will get is 35% is 20%. So there is a 20% chance, or 1 out of 5 chance, that if you randomly select 2 stocks, you will get an average of 35%. So So that's how we interpret the probabilities in the sampling distribution of the sample mean. The sampling distribution of the sample mean has the following properties. First, the average of all possible sample means is equal to the population mean, and that is shown here in this equation. So mu sub x bar refers to the average of all possible sample means in the sampling distribution. And according to this equation, again, the average of all possible sample means is equal to the population mean. So in the example shown earlier, if we get the average of all the 15 sample means that we constructed, that should be equal to the average of the entire population of just 6 elements. So that's the first property. Now this property allows us to say that the sample mean is an unbiased estimator of the population mean, because the expectation or the average of all values of x bar is equal to the parameter it's estimating, which again makes x bar an unbiased estimator of the population mean. Now, another property of the sampling distribution of the sample mean is that the population is more spread out than the sampling distribution of the sample mean. So if you compare the histogram of the probability distribution of x to the histogram of the sampling distribution of x bar, you'll see that the histogram of the probability distribution of x bar is wider or is more spread out as compared to the histogram of the sampling distribution of the sample mean. And mathematically, that is explained by the difference between sigma sub x bar and sigma. Again, sigma is the population standard dev of all values of the random variable x, while sigma sub x bar is the standard dev of all possible sample means. So again, this computes for the standard dev of all values of x, while this one computes for all values of x bar. And to compute for sigma sub x bar, that requires to divide the population standard deviation by the square root of n, which makes sigma sub x bar naturally lower than the value of sigma. Now, this is just one formula when computing for sigma sub x bar, and this is used only if capital N over small letter n is at least 20, or if the population is relatively huge compared to the sample size. Now, this equation can allow us to conclude if the population can be considered infinite or not. So if this condition is satisfied, we can loosely call the population infinite, which requires the use of this simpler formula. Now, if capital N over small letter n is less than 20, we can call the population finite, and the formula for sigma sub x bar will also be different. So that's the same formula here, but we have to multiply that to another value. That's the square root of capital N minus small letter n over capital N minus 1. Now, this value that we are multiplying to your original formula is known as the finite population correction factor. So this one, again, is known as the finite population correction factor. And as mentioned earlier, this is only multiplied to the original formula if your population is considered finite. Now, the third property of sampling distributions of the sample mean is about the shape of the graph of the sampling distribution. So here in this set of graphs, we have three different normal curves. In the first one, we can see the graph of the population of individual mileages. So here, it shows us all possible values of x with mu as its average, while the second one shows us the graph of the sampling distribution of the sample mean if n is equal to 5. So again, this doesn't show us all values of x, but all values of x bar. And this is specific to the possible sample means if the sample size is only 5. Now, if you compare that to another sampling distribution of the sample mean, if you have a bigger sample size, in this case that's n equal to 50, we can see that the shape of the graph is also different. So it's now taller as compared to the first one, and in terms of the spread, it's narrower compared to the sampling distribution of the sample mean when n is just equal to 5. Now, this can be explained by the central limit theorem. So, as you know, the central limit theorem allows us to make conclusions about the shape of the distribution of the sample of the sampling distribution of the sample mean depending on two factors. First, we look at the distribution of x. We look at how x, the random variable, is distributed. Also, we look at the sample size. So looking at these two factors will allow us to make conclusions about the shape of the graph of the sampling distribution of the sample mean. Now, according to the central limit theorem, if the population of x itself is normally distributed, then regardless of the sample size, if your sample size is small or large, the sampling distribution of the sample mean will be exactly normally distributed, which means that the graph of the sampling distribution of the sample mean will be bell-shaped and symmetrical. Now, according to the central limit theorem, if the population of x is not normally distributed, meaning the distribution of x is not bell-shaped and is not symmetrical, as long as the sample size is large enough, we can say that the sampling distribution of the sample mean will be approximately normal. So the graph of the sampling distribution of the sample mean will also look relatively bell-shaped and relatively symmetrical. Finally, if the population of x is not normally distributed and the sample size is not large enough, then it means that the graph of the sampling distribution of the sample mean is not normal, meaning the graph is not bell-shaped and it's also not symmetrical. So here is again the demonstration of the central limit theorem. So in this example, we can see that the graph of the population is not normally distributed. This is bell-shaped, but this is skewed to the right. It's not symmetrical. So if your sample size is large enough, then the graph of the sampling distribution of the sample mean will still be relatively normal or approximately normal. So it's still bell-shaped and it's still symmetrical. Here's again another example of the central limit theorem. If you look at all these graphs, all of these are non-normal and all of these are graphs of values of x. So the population graphs are not normally distributed, and here we have graphs of sampling distributions. So these are graphs of values of x bar, but for increasing sample sizes. So here, for the sampling distribution with a sample size of 2, we can see that the graph slightly changes, but as you can see here, the graphs are not normally distributed yet. If you increase the sample size from 2 to 6, we can see that the graph improves in terms of the shape and in terms of the symmetry, but not all of them are approximately normal. Finally, in this set of graphs, once you reach a sample size of 30, we can see that the graphs of the sampling distributions of the sample means are now bell-shaped and symmetrical. And that's actually the basis for us to say if your sample size is large enough. Empirically, if your sample size reaches at least 30, and the population of X is not normally distributed, the sampling distribution of the sample mean becomes approximately normal or approximately bell-shaped and approximately symmetrical. Now, in the same example that we showed earlier, I'll show you the properties of the sampling distribution of the sample mean that we just discussed. Again, the first property says that if we compute for the average of all the sample means that we constructed, it will give us the same average of the population. So here again, we have all possible sets of 2 from 6. So we have 15 different combinations of 2 out of 6. And we computed for the sample mean of each combination, and we got the following sample means. Now, to verify, we can get the average of all these 15 sample means, and according to the property, that should also be equal to the population mean. So when computing for the average, we will get 35%, and again, that's equal to the average of the 6 stocks. So again, that's the first property, which makes the sample mean, again, an unbiased estimator of the population mean. Now, the second property is about the standard deviation of the population compared to the standard deviation of all sample means. So first, we need to compute for the standard dev of the population. So I'll use the function stdevp of these 6 values, and I'll get here the value for sigma. Now, we will compare that to the standard dev that we will get using the formula that was shown earlier. So again, in this example, we have these 15 different sample means. So we can actually use these 15 values to compute for the standard dev of all sample means. So using the same function, that's stdevp. So these are all the sample means. That's why I'm also using the population standard dev function. And if I compute for that, I'll get 0.1080. Now the two values here are different because again, this is sigma, while this one is sigma sub x bar. And again, you can see that sigma sub x bar is lower than sigma. Now, if we use the formula that was shown earlier, we can compute for this value using the value of sigma, small letter n, and capital letter N. So in this example, capital N is 6, small letter n is 2. So capital N over small letter n, or 6 over 2, is just equal to 3. That's less than 20. So to compute for sigma sub x bar, we have to use the longer formula. So again, the longer formula is sigma over the square root of n. So we have sigma computed here, and then we will divide that by the square root of the sample size, which is 2. So this is the first part of the formula. But again, we know that this is not complete because the population is finite. We have to multiply this by the finite population correction factor, which is again the square root of capital N minus small letter n over capital N minus 1. So capital N here is 6, small letter n is 2. So for the numerator, that's 6 minus 2, or 4. And we will divide that by capital N minus 1. So capital N is 6, and then we subtract 1 from 6. The denominator should be 5. So computing for this function, we should get the same value here. And again, we can see here that the two values are equal. So that's an example of the use of the formulas to compute for the mean and the standard def of all possible sample means. Now, here in this example, I used a different sample size. So instead of getting a sample size of 2, we can also get a sample size of 3. So if you compute for the number of combinations of 3 out of 6, you will get 20. So these are all the 20 possible combinations of 3 out of 6. So you can get stocks A, B, and C, or you can get stocks A, B, and D, or A, B, and E, and so on. Now, using a similar approach, we can compute for the sample mean of each combination. So the average for the first combination of 3 is 20%, and then I'll do that for all the values for all combinations. And again, to demonstrate the first property, if I get the average of all these 20 sample means, I'm also getting 35%, which is again equal to the average of the population. Also, I can compute for the standard dev of all the sample means. So computing for that gives me 0.074. Now we can also compute for this using the same formula that was used earlier. So here, even if n is now small letter n is now equal to 3, capital N over small letter n, or 6 over 3, is equal to 2, and that's still less than 20. So we still have to use the second formula. So again, that's sigma, the exact value, over the square root of the sample size. And here, the sample size is now different. It's now 3. And then I'll multiply this again to the finite population correction factor, which is the square root of capital N minus small letter n. So now that will be 6 minus 3, or 3, over capital N minus 1, which is still 5. So computing for that again gives us the same value, which is 0.0764. Now, another kind of the sampling distribution is the sampling distribution of the sample proportion. So it's very similar to the sampling distribution of the sample mean, wherein this is also a probability distribution of the population of sample statistics. However, instead of showing us all possible values for the sample mean, from the term itself, it shows us all possible values of the sample proportion. And similar to the sampling distribution of the sample mean, it's possible to have different values for the sample proportion because we are still getting small letter n from capital N. So for each small n, you can compute for the proportion that falls within a certain category, and then you can do that for all possible combinations of small letter n from capital letter N. So again, this is commonly used if the population of measurements represents values of a qualitative variable, and since it's a qualitative variable, we don't compute for the sample mean, instead we compute for the proportion. And these are the properties of the sampling distribution of the sample proportion. So similar to the first property of the sampling distribution of the sample mean, the average of all possible sample proportions, or mu sub p hat, is equal to the population proportion pi itself. So again, once you've computed for all the possible values for p hat, and you compute for the average of all those p hats, you'll see that the average of all the p hats will be equal to the proportion from the population. Now we can also compute for the standard dev of all possible sample proportions, or sigma sub p hat, using these two formulas. And again, the first formula, the square root of pi times 1 minus pi over n, is used if the population is infinite, or capital N over small letter n is at least 20, while the longer formula, that's the original one, times the same finite population correction factor, is used if the population is finite, or if capital N over small letter n is less than 20. Finally, we still have the central limit theorem applied to the sampling distribution of the sample proportion. But instead of looking at the distribution of the population of X, we only look at the sample size. So the sample size here, we don't compare that to 30 to determine if the sample size is large enough. in sampling distributions of sample proportions, we can say that n is large enough if n times pi and n times 1 minus pi will give values that are both at least 5. So again, if you multiply the sample size to the population proportion and you multiply the sample size to the complement of the population proportion, and both values will give you values that are at least 5, then we can say that n is large enough. Therefore, the sampling distribution of the sample proportion is approximately normal. So those are the properties of the sampling distribution of the sample proportion. Now again, I'll show you another example of constructing the sampling distribution, but now involving sample proportions. And then we will see the properties that we have already discussed about sampling distribution of sample proportions as well. So in this example, I have 5 elements in the population. So my population is composed of the top 5 officials in the country, and then we also have their sexes. So for the president, that's male, vice president and chief justice are both females, and then for senate president and house speaker, both are males. So the population is composed of 5 elements, so capital N is equal to 5, and among the 5 elements here, 2 of them are females. So to compute for the proportion of females, that's just 2 out of 5, or 40%. So 40% will serve as the value of pi, and 5 is equal to n. Now to construct the sampling distribution of the sample proportion, let's consider a sample size of 2. So here again, we are getting 2 out of 5, and here are all the possible combinations of 2 out of 5. So it's possible to get president and vice president out of the 5, or the president and the chief justice out of the 5, and so on. And for each combination, we can compute for the sample proportion of those who are females. So in this first combination, president and vice president, 1 out of the 2 is female, so the sample proportion of females there is 50%. For president and chief justice, again, only 1 of the 2 is female, so the proportion of females there in that combination is also 50%. For this one, both are females, that's why the proportion of females is 1 or 100%. And then for president and senate president, both are males, that's why the value of the proportion is 0. Now, using these values, we can construct the sampling distribution of the sample proportion. So again, the sampling distribution of the sample proportion requires the values for the sample proportion and their probabilities. So here we only have 3 unique values for the sample proportion. We have 0, 0.5, and 1. 0 appeared 3 times. So again, we can construct the frequency distribution first. And then 0.5 appeared 1, 2, 3, 4, 5, 6. That's 6 times. While 1 only happened once. So if you get the sum, that's equal to 10. Because again, we have 10 combinations of 2 out of 5. And to compute for the probability, we just have to get the relative frequency. And here we have 30% for 0, 60% for 0.5, and 0.1%, 0.1 or 10% for a sample proportion of 1. So again, to interpret, this particular row means that if you randomly select 2 out of the 5 government officials, top 5 government officials, the probability that 50% of the 2 or half of the 2 are females is 60%, or there is a 6 out of 10 chance that 1/2 of your sample of 2 will be females if you randomly select 2 out of the 5. So that's how we construct and interpret the sampling distribution of the sample proportion. Now to show us the properties of the sampling distribution, again, we have here all possible sample proportions. And if we get the average of all these possible sample proportions, we will get 0.4, which is again equal to the population proportion itself, making the sample proportion an unbiased estimator of the population proportion pi. So that's the first property. Now for the second property, again, we can compute for the standard dev of all the possible sample proportions. So again, that's STDEV P of these 10 sample proportions, and you'll get 0.3. Now, another way to compute for this is through the formulas that was shown earlier. Capital N here is 5, small letter n is 2. So 5 over 2 is obviously less than 20. So to compute for sigma sub p hat, we have to use the longer formula. So again, the longer formula requires the square root of pi times 1 minus pi over n. So here, that's pi. Again, the numerator is pi times 1 minus pi, or in this case, that's 0.4 times 0.6, and then we divide that by n. And here, the sample size is 2. So that's the first part of the formula. And then we multiply that to the finite population correction factor. So again, that's capital N minus 1 and small letter n, the square root of capital N minus small letter n. So that's 5 minus 2 or 3 over capital N minus 1. So that's 5 minus 1 or 4. So again, when we use the second formula, you can see that we got the same value as when we used the STDEV formula in computing for the standard dev of all the sample proportions. Now we can also do that for a bigger sample size. Let's say your sample size is now 3. So if you randomly select 3 out of 5, these are all the possible combinations. And I also have here the respective sample proportions for each combination. So to construct the sampling distribution, again, just list down all the unique values. So we have here 3, 0, 33%, and 0.67. And then get the relative frequency to get the complete sampling distribution. At the same time, we can also see here the properties of the sampling distribution of the sample proportion. So the average of all these 10 sample proportions is still 40%. That's equal to the population proportion. And the standard dev of all these sample proportions is 0.2. And again, another way to compute for this is through the formula that was shown earlier. That's again the square root of pi times 1 minus pi, or 0.4 times 0.6 over n. And here n is now 3. So we divide that now by 3. And then we multiply this further to the finite population correction factor, which again will be slightly different. So that's capital N minus small letter n of 3. So that's 5 minus 3 or 2. And then divide that by capital N minus 1 or 5 minus 1 or 4. And again, we can see here that the formula we used gave us the same standard deviation. So these again are examples of constructing the sampling distribution of the sample proportion and verifying the properties of the sampling distribution of the sample proportion.